go today to meet any good.
Yeah, oh, utility monitoring or
Yeah, exactly. It's like straight to the No, they do monitoring wirelessly, and then they provide like analytics to Yeah, is that a 5-person?
I think that thing works with the squares. I'm not having it cleaned down, but that works. Sum of squares. You can drive it down to up to the point where it cannot factorize anymore.
See, I thought it was something like that. We still have to figure out why that was.
Yeah, I don't have it clear, but all right.
Sometimes.
So today we talk about boosting. We started that on Tuesday, right? While you guys still work on the previous homework, so that's a little bit of difficulty to get your attention here while your actual focus is somewhere else. So I expect some people will have to go through these videos and notes over the break because everybody's busy right now fitting Gaussians, and so that's a trouble, right? But we have a week of break next week, and we don't have classes. That's good. You get a little bit of a week without me. Don't miss me too much, because I'll be back.
There's the videos too.
Yeah, but maybe some people will say, okay, I don't want to see his face for a week, so I want to see the videos, right? But there will be some office hours. Not every day. We'll ask the TA to post on Piazza probably 2 days next week. If you want to come in, you should tell them you want to come in or not, so they don't come for nothing. I expect during next week we're still talking about Gaussians. I don't expect to move to the next homework, but the next homework is online right now. If you click there, you can check it out. It's about testing and bagging and all the things that we talked this week and after the break. Right? It won't be due. So if you start the homework, 5, right after the spring break, you'll have time to finish. First things first. You should put your name on that note. You put my name. I didn't write the note. You did, right? I'm flattered that you put my name on it, but you should put at the minimum yours and mine, but I think you should be yours because you wrote it. So he figured out that derivation from EM or flipping coin. So I'm going to make a short parenthesis that's not related to boosting. It's EM for coin flips. So that's D coin flips. Remember problem, what is it, 5 or 6 in the current homework 4. The distribution of a flip, P of probability of, so this is X is the number of flips. X is X1, X2 up to XD. Each one of those are 0, 1. 0 means tail, 1 means head. So I'm flipping a coin. So I'm picking a coin with bias QK, that is the probability of a head for that coin. I have K coins, I'm picking one, I flip it D times, and I'm getting a sequence of flips, each of them it's a head or tails, and I'm going to call size of X is the number of heads. So in other words, how many of the flips are ending up being a head. The probability of seeing such a sequence, by a sequence I mean seeing that many heads, not the exact sequence, because I don't care about the order, which ones are tails, which ones are heads. In a sequence of D flips for this problem, I'm only going to care how many heads are there. If I am to care about the order, it becomes a different distribution. The probability of any sequence will be something like, if this is a head, it's Q times 1 minus Q times 1 minus Q, so on and so forth. It's exactly a probability. But if I'm to combine all the sequences that have the same number of heads, I'm only asking what's the chance of seeing that many heads in any order. That will be the binomial distribution, right? So what is it? Is D choose how many heads you have. This is the N choose K, combinations of that choose K. QK at how many heads you have, and 1 minus QK at how many tails you have. That would be D minus X, right? It's a typical binomial distribution with two outcomes. Otherwise, it would be multinomial. So that's one of the probabilities. Now, EM, it's for a mixture. So the mixture is probability of seeing something. It's the sum over all components of pi k probability that's from that component of seeing that thing given that particular coin. This is the sum over all coins, because I don't know which coin I'm going to pick. This is the same process like with Gaussians. We talk about this, just the generative function for each component is not a Gaussian, is a binomial. So I've done a lot of E steps was computing that ZIK, right? And we said the formula for ZIK is the same like in a Gaussian, like in any mixture, the membership. It was what? It was the probability of X being QK times pi k divided by normalization, right? So that would be the sum of all this stuff over all possible k to sum to 1. It's like taking all the possible numerators, sum them up, so when I divide, I get the distribution. In the M step, we have to estimate two types of parameters. One type of parameter is the pi k, is the mixture coefficient. This is the same like in Gaussian. In all mixtures, this is, or in most mixtures, it was the weighted average, right? So that was what? The sum over all the data points of memberships divided by n, right? The size of the cluster. The best analogy, like I said on this problem, is to make it with k-means. If you don't want to follow the math, follow the k-means mechanical procedure. What do k-means do? The size of the cluster, it's how many points are there. Those will be 0, 1 in k-means, not probabilistics, divided by the total. The other parameter is the parameter of this distribution. For Gaussians, the internal parameters are sigma and mu's. For these coins, we don't have sigma and mu's, because those are not Gaussian distributions, those are binomial distributions. And this is where I made a mistake a week ago or so. I put the formula for QK, but I call it pi k. So Kim and somebody else pointed out, hey, you mixed up those parameters. And I asked you guys to derive this formula, take derivatives, work it out, see what happens. So the formula is the sum of ZIK times the sum of XI, how many heads I have there, divided by the sum of ZIK, that's the probability of membership, times D. And I think you put online the derivation of this. So if you don't want to do the math yourself, again, this is the same like Gaussian, this is the same like Gaussian. Of course, a different probability function here. That's the binomial one. This is different, the QK from the binomial distribution. The math is not required. You should be able to implement those formulas for problem 5 and get the answer. What are the answers again is the biases and the mixture coefficients, right? But if you want to do this math, you can try it. If you want to see it without doing it, I think he posted on Piazza. How do you get to this problem? So I want to make that correction right now. But I don't want to spend too much time on it. So that's that. Now let's go back to boosting. And the first thing first, I asked you last time to prove something for me, which was the square loss is what? Noise squared plus bias squared plus variance. Anybody figure that out? Why that is? You did, but no post on Piazza yet. All right. Anybody else? Like, it's not just the math that we need to do as an equation, it's just we have to actually figure out what those quantities are, mathematically speaking, right? So how do we have few equations here that I want to show you, and you should still put on Piazza your derivation if it matches this one. I'm going to put those equations up and let's see if we can follow them. Here's how I'm going to work this out. This is an important thing. like I said, this equation appears in many contexts. It's not just in the boosting, bagging, what we're doing now. For calibration properties and for all kind of regression functions and arguing about losses and what losses are doing, you will need an equation like this. So it's important to see it and to follow at least the basic case.
Maybe you have, but can you please give example to noise?
Right, that's what I'm going to define first.
I think the last question said that a patient with 2 diagnoses is a noise, blah, blah.
Oh, you mean real noise, like in practice?
Yes.
In practice, noise comes from many places. One sort of obvious noise is when people mislabel the data. A doctor puts the wrong diagnosis. A person mislabel a document with a tag or an image with something in it. Another kind of noise comes from shifting. It's not a mistake, it's just before today I did things in a certain way, and after today my definitions of my workflow or my language has changed. I'm not calling this anymore CS6140, I'm calling it, the college changed the names of the courses, okay? And all of a sudden it has a different label. It's just a shift in the data. That would be a simple example. It's a one-to-one map, but in many cases, things that were called in certain ways are called in more granular ways, and then it's not a one-to-one mapping. Data has shifted. In a patient record, if I'm the doctor, I may write a different note than if she's the doctor, right? Although we did the same exact thing, who writes the note has some little small interpretability of the procedure and might result in a different language. Language itself changes. People who come from different countries, like most of us, they tend to translate in English in slightly different words or jargon. So especially for text, it's a common problem to have noise in it. Other mistakes might have noise or what appears to be noise, but it's not necessarily noise. It has to do with too little data. If I have too little data, the relationship between features and labels may not be perfectly determined. So it may appear a little random or a little bit unclear why that is. Once I have more data, this uncertainty, this particular kind of uncertainty might reduce. But in here, we're looking for a very mathematical explanation. So I'm not dealing with real data here. I'm just trying to prove this in a very strict mathematical sense. So here's what we're going to do. We're going to say I have a classifier, h of x is the prediction. Let me see. Here, y of, which I'm going to call f of x plus epsilon is the truth. So f is my generative function. F is the God's function that assigns from an x to y. This is the generator for labels. And this is the noise. So there's some true label that's being assigned. Think about the quantity. Y in here is a quantity, that the target is a salary. But then there is some random noise that takes the actual truth and perturbs it into what I actually see. This is observed. This is observed. This is the truth here. And this is the noise. So if you want to really imagine this process in a generative sense, there is a divine presence that establishes the truth. For any patient, the divine presence establishes exactly the truth. F of x is the real truth. But then what you observe in data is the truth plus some error that may come from many places of different kinds. Mislabeling, not seeing properly, mistaking one patient for another. Many things happen in the real world, right? So if I have that, how would I write this equation here? What would this equation be? What is the square loss? Yes.
Whatever n times the sum.
So I'm going to write it as, I can write it as a sum or as an expectation. So the square loss over data points is the difference between who and who.
Y and
H is my predictor and
Y.
Y. Because I'm measuring the square loss against the observed truth, right? That's what you guys do for training. You don't have access to the real truth, right? So that's the square loss. I can write it as an expected value, right? Instead. So expectation of h of x minus y squared. What is the noise? Noise is what perturbs the real truth into what you see as truth. So even though you see tags or salaries or diseases or spam versus not spam, there is a chance that what you see, the y, is not exactly the truth. So who's noise squared?
Which one is what?
Which is no. Noise is not related to h. Noise is in the data. H is the predictor, the classifier I'm training. Noise is there whether I want to or not to be there. So who's the noise? Epsilon. Epsilon is the difference between who? Y, which is what I see, and F, which is the actual truth. We are assuming the actual truth exists. That's a philosophical conversation. In data, sometimes it's hard to tell what's the actual truth, right? I have a patient, a doctor puts a diagnosis to it. What diagnosis corresponds to what? No. The diagnosis, this person is sick, has diabetes. If you get that data, what is that diagnosis? What quantity here? Y. Now, what is the actual truth? That's a philosophical question, like who knows how sick this guy really is, right? I mean, many things in practice and in reality are not black and white. Somebody may have some form of diabetes that's not very clear diabetes, but it's on the path to become a diabetes if you eat more sugar things, right? So a lot of things are not crystal clear sometimes. But we assume there is an actual truth, f of x. Okay, who's the bias? This is kind of the performance of my classifier. So who's that? So it's a sum of, let's write it as a sum of the data points. I think this might be a sum too. So who's the bias?
H of x minus f of x.
H of x minus f of x squared. So that's my prediction versus the actual truth. And what's the variance? Hmm? Variance of what?
Would be the variance of h of x, which would be h of x squared minus, or like h of x minus the mean.
So it's sum over h of x minus
The
the
mean
expected
h of
value
x
of h of x. Is that it?
squared. Yeah, that's correct.
So this expectation with respect to what? Again, this variance can be a confusing thing. How do I have variance? When you train decision tree, you don't get variance. Right? You get an exact thing. Well, why we say it varies? Varies by what? What can make your decision tree have variance? If I train on a different training set, I may get a different tree. Right? Right. I can get a model depending what data I have. The more data I have, the less variance I would get. Right? I think this is still a sum over data points. Right? And when I take expectation, that will be epsilon squared plus expected of h of x minus f of x plus expectation of h of x. That's a variance. Right? I still don't feel like proving it. Proof is here, 2 slides. I would like you guys to try to prove it. It's not that bad, like it's look, a few lines of math. Compared to the other stuff we've done, it should be easy. So now that we have a mathematical instantiation of what this theorem says, maybe you guys can work out these quantities using the formulas for expectations and variance and get it done. Again, this is a simple thing that anybody can do. It's not a complicated thing. You should remember the equation, because the equation keeps appearing in all kinds of instances. It's not just this setup where I'm trying to. My use of this equation here is to say, how do I, what did I say last time? How do I don't increase variance, but decrease the bias, right? That was my point last time. Because I'm gonna keep going with boosting here. So ensemble of one split trees. So we call this boosting. And we said the f of x, the classifier, is sum lambda 1 times the first tree, right? Plus lambda 2, or was it alpha?
Yes.
Of the second tree, plus, depends how many trees I have, one split trees, or if I want just in general simple weak learners. I don't have to put trees in there. Trees are the simplest possible procedure, one split trees, that we even visualize in data, right? A one split tree is just a line that's following a feature, right? If it's x1, it cuts the data that way. It says you either go that way or that way, or it could be a feature this way. So any simple decision tree that is called a decision stump is really picking one feature, one threshold, separated data, that is done. Simplest possible classifier.
Suppose you go like one more level down, would it still be considered like a simple classifier?
That's up to you to define. People have used very complex classifiers in their neural networks. So it's not a strict what it means. It's the idea that, again, we said this last time, going down in the tree increases variance. That is the dependency to that particular training set, right? I can minimize the training error by going down the tree. Easily I get 0 training error. But that's has high variance in the sense that for any training set I'll use, I'll get a different tree. So by not doing that, I'm keeping things simple, and we have a large argument last time that this tends to actually decrease variance. Remember? We said that if you get, even though those things are correlated or uncorrelated, variance will not increase this way. Doesn't matter how I'm producing the trees. As long as they are relatively simple, if I add up a bunch of them and average the result, that always decreases variance. If those tends to be independent, it decreases the variance even more. We said that the variance of x1 plus x2 plus xn, if those are independent, divide by n, will actually be the average variance, again, divided by n. So it's a known thing in statistics, I think you've seen it before. By averaging independent variables, you're definitely going to decrease variance. But even if they're not totally independent, variance still gets decreased. So with that guarantee, and it's a very nice guarantee because it's true for any trees, the variance decrease doesn't imply that we have to construct the tree somehow. We're going to focus with boosting on the bias, which is the performance. So we know we're not going to increase variance if we add up trees, therefore we focus on how to increase performance. Right? That's what we've done. And we had an algorithm, right? AdaBoost. Let's recap that algorithm. I'm going to put it here quickly without talking about it again. So what was it? AdaBoost. So starts round 1, 2t. It has dt, the weight or importance distribution over data. In particular, d1 is who? The first. It's 1 over n, right? The first distribution of importance over data, it's uniform. So what does AdaBoost does? The first thing, it trains a weak learner. The only thing different than in your homework 1, in homework 1 you train a tree, you're going to do the same thing here, just one split tree, so you just do the first split and stop. But it trains it with respect to that distribution. It pays more attention to the things that have higher weight. So how do we write that down? So train weak learner. That again, that for you it's going to be a one split decision tree. So we're going to call that HT because it's the weak learner at this round, right? This is the first tree, then the second tree, then the third tree, so on and so forth. And it has the error. It's like accuracy, but it's weighted for the data points that have higher weights, right? So I go over all the data points. I sum up 1 for every time HT of X is different than the Y, right? For every data point. But I also multiply with who? dt of xi. So in other words, the data points that have large weight count a lot for the error to get them right. And the data points that have low weights, almost no count at all. It's focusing the classifier towards the points that have higher weights, right? This error will be, obviously, if the HT of X is Y, that is correct. And then the whole predicate becomes 0. So it doesn't matter the weight for the ones that got it right, right? All right. So I have this epsilon. That is the error at that round. Is the error for that tree, again, weighted for the importance. Then I compute this coefficient. Coefficient for that tree in the ensemble. What is that? What's the formula? I think we had it last time. Was it 1/2 in the front? ln of?
1 minus epsilon t.
1 minus epsilon t divided by epsilon t, something like that. So this is called the log of odds in statistics. But just for us, quickly, what happens if epsilon is 50-50? Like it's a random classifier. What will this whole thing be? 0. So that makes sense, right? If you get a random classifier, you get that classifier doesn't contribute to your ensemble. What happens if I have a very good classifier here? Error is very, very small. So this is 0.0001. What do I get? Big coefficient. That makes sense, right? And if this epsilon is very high, this acts like an inversion. It says, well, if epsilon is very close to 1, by flipping this classifier, I'm in a binary world here. I'm going to assume the Y belongs to 0, 1. And also the HT of X belongs to 0, 1. So binary world, both the weak learner and the label are either black or white. So if I have an epsilon that's very high, I have to flip this classifier to reverse it to make something out of it. And this actually reverses it, right? This will assign a negative coefficient, which means count it backwards. And then finally, what do I have to do? Update who? D, right? So the next dt plus 1 of the data point is going to be the old dt for that data point times what we were doing. If you are correct, you have to decrease the weight, right, for correct points. And if you are incorrect, you have to increase the weight. So here I have epsilon at minus alpha t, which is, by the way, who? Square root of, right? If ht of x is y, that is correct, right? And the other way, if ht of x is not y, that is means incorrect. So assuming for a moment that the epsilon is below 50%, is this, we want this to be, if I'm incorrect, I want to be an increase, right? So if epsilon is below, say, it's 35%, do I get an increase in here in the distribution? So if epsilon is below 50%, which quantity is bigger, 1 minus epsilon or epsilon? 1 minus epsilon is bigger, therefore the square root is bigger than 1. Therefore this is an increase. And this one here is a decrease. And of course I have to normalize with something at the round. This is normalization. So sum to 1, right? Since I want to keep a distribution. That's the ADA boost algorithm. Loops for a certain number of rounds. You can either have a fixed number of rounds, like t equal 300, or we can have flip it until convergence. And we can define convergence, for example, as what's the natural getting stuck in here? How this algorithm gets stuck. Meaning, if I make the update, I don't actually update at all. When this algorithm will get stuck, when the update doesn't do anything, it remains the same distribution over data, right? So to remain the same distribution, what needs to happen here?
Alpha gets very small.
Alpha gets,
Small.
alpha can be positive or negative, right?
Becomes very close to 0.
Become very close to 0 because E at 0 is 1. But alpha close to 0, it's equivalent to epsilon being 50%. So getting stuck means what? dt is very close to dt plus 1, right? Same distribution, which is the same as saying alpha t is close to 0, which is the same as saying epsilon t is 1/2. These are the being stuck in ADA boost. And you can see that if those things happen, they happen together. Right? When one, this makes no progress, that's 0, that's 50%. And you can tell in my ensemble that tree that I just got at that round will not contribute anything because alpha t is 0. And I'm in the same exact spot like I was in the previous round. The distribution didn't update. My tree is useless. My alpha is 0. So I can keep doing that, but as long as my weak trainer here cannot produce something better than 50% error, this is looping infinitely with no progress at all. So getting stuck really depends on, can I produce a weak learner that's better than random? That's really what it comes down to.
I feel like we talked about this last time, I can't find the names. How close to 0?
So as long as there's a theorem that we stated last time, now we're going to prove it. As long as it's not arbitrarily close to 0. So even if the difference is 0.0001, like in calculus, but not closer than that, where that quantity is fixed. Could be any size small, but fixed. So as long as, so let's put the theorem in here. This is training error. That says the probability, so the training error is the probability over the data set of f of x being different than y. So that is the same as saying the sum 1 over n, sum over the data points, counting the mistakes, f of x is not y. This is smaller than the product over all rounds of boosting of square root of 1 minus 4, where gamma t. Gamma t is just a transformation of alpha. So let's write here, for the purpose of this theorem, gamma is 1/2 minus the error. And I said here for math reasoning, we don't need this particular term. It might be easier to think of this as, what do we have here? 2 gamma either this or this serve the same purpose for this theorem. So if you understand my concept that I want to, how do I drive this error to 0 from here, that's fine, you don't need that term. But applying this inequality, which I put on board last time, may be more obvious why this drives to 0. The idea here being, this is obviously a positive quantity. So if I show that one of these terms goes to 0, the error will go to 0 too. So what is this really saying? It's a product of things, right? And I'm saying every single one of them is lower than 1, because it's 1 minus a positive quantity, right? So I say this product of t equal t of square root of 4 gamma t squared. Again, gamma is how close it's epsilon to a half. That's what gamma is. This limit of this when t goes to infinity, I say goes to 0 with one condition. If I drive enough rounds of boosting, I'm making a product of numbers that are smaller than 1, right? So if I multiply numbers that are smaller than 1, eventually the whole thing will go to 0, right? With one condition. The condition is that these numbers that I'm multiplying cannot be arbitrarily close to 1. Right? So think about this way. Here's the 1/2, right? And here's the epsilon. Gamma is this difference, right? It's between 1/2 and epsilon. If I can guarantee that there is an interval around 1/2, that epsilon will never get in that interval. In other words, the weak learner, it's not 50-50. There is a buffer here of guarantee that's saying you can get epsilon on either side. We already discussed this. If epsilon is too high, I can flip the classifier and get it, the other epsilon. If I have a 51% error, I can flip it, make it a 49, because it's a binary case, right? This is that distance that before, last time I called 0.000001. If I need a guarantee that epsilon will never get that close to 1/2. If I have that guarantee, that means what's going to happen with gamma? If epsilon never gets that close to 1/2, gamma will never be that close to. Gamma is epsilon minus 1/2. So gamma will never be that close to 0, which means 4 gamma squared will never be that close to 0, which means 1 minus that will never be that close to 1. As long as these numbers are never that close to 1, by multiplying enough of them, we get something that gets very close to 0, right? Even if this is allowed to be 0.9999, eventually if you multiply 0.9999 with itself enough times, it still goes to 0, because any exponential with a base smaller than 1 will drive to 0. Hands up is with. Good. So that is this theorem saying, if you can guarantee that the weak learner procedure, the training, will never get close to 0.5 for any distribution. So that is where I may need more than one split. Maybe ADAP gives me a distribution that no matter what feature, by what threshold I split it, I get 50-50. Then it means if I stick with one split, I can make progress. Because any split by any threshold will have an exactly 0.5 error, right? And that means, like I said, the whole loop here is getting stuck. If I get error 0.5, alpha 0, update does nothing, I can't make progress that way. Maybe that would be the time to say, okay, how about give it 2 splits now? If I really want to make progress, I have to increase the complexity of the weak learner, because any one split gives me nothing. Right? Suppose that happens. Suppose this, I get the guarantee that gamma is never that close to 0, aka epsilon, it's never that close to 0.5. What is this theorem saying again? The training error will go to 0. That's nice, right? Don't we want training error to go to 0? I mean, why not? I mean, we wouldn't want training error to go to 0 if we overfit, aka if we increase variance. But we already said this process is unlikely to increase variance, and if that's a given, why not drive the training error to 0, right? It's that magical. Boosting increases performance by quite a lot without overfitting, at least initially, even if the weak learners are quite weak. Each one of them, we had that example last time on the board, every line had a performance 70%. Yet when we put 3 lines together, we get performance 100%. So that's what happens. That's what's going to happen in your Homo 5. You can tell that initially, you're going to get the best weak learner possible, right? Because you train it with a uniform distribution. You train the first split. That performance is going to be 75%. Because there's no one feature in the spam-based data set that gives a high performance. But then you'll see once you train 100 rounds of boosting, that performance gets to like the best performance you have seen in Homo 1. Boosting would probably would be as good as the first 3 that you had, or the regression algorithm, or the naive Bayes and all that. I would expect boosting will be at least as good as those. And another thing, this theorem here means one of 2 things might happen. There's only 2 possibilities for boosting to stop. What are the possibilities? Either training error goes to 0, or it's stopped, which means the error that I'm producing with my learner is. So that's the essential ADA-boost theorem. When you do boosting, 2 things will happen. Either you manage to get bias 0, training error 0, or your weak learner gets stuck, cannot make progress anymore. And we know why that is. As long as these gammas are not 0, this is guaranteed to decrease to 0. Of course, we have to prove this theorem.
Is there any method through which we can unstuck it?
Yeah, I just said that. If you see 0 as the best you can do is a split that gives you 0, you gotta allow for more complex classifier if you want to keep going. Well, the moment you see 0, there's no point continuing, because that's no progress. You're in the same spot. You gotta increase the complexity of the weak learning. You gotta make this 3 here, say, okay, I'm gonna give it 1 more split. Because 1 split trees will not make it anymore. I think that answers somehow your previous question.
Yeah, I was gonna ask you if you could just run something simple, get stuck, drop it, and keep on going.
Yeah, eventually you're gonna have to keep increasing, but at some point it's not worth decreasing the training error, right? The moment we start increasing the classifier, even though that way we're gonna decrease the training error, it's likely overfitting and is not decreasing the testing error anymore. So what people do in practice, they run a validation set on the side, and it only makes sense to increase the complexity if you decrease both errors. If you decrease the training error, which you guaranteed to be able to do by increasing the complexity, but not the testing error or validation error, it just means now you start overfitting and it doesn't go any good.
Can you use different weak learners?
Yes. This procedure, that's a very good point. I mentioned it when you guys already left the room last time, or were about to go. This procedure doesn't imply a particular training algorithm or the same training algorithm. Every time I call this, think about this as a wrapper. It doesn't tell you how to train your weak learner, as long as epsilon t is not 50-50, or equivalently alpha t is not 0. As long as you can respect the current distribution of importance, and you can give it a classification, an HT, a function that is better than 50%. It doesn't have to be the same like previous round. It doesn't need to know how it's computed. This procedure doesn't assume that's a tree or anything. It can pick one at random. You don't even have to train it. Right? Imagine that somebody says, you know what, I'm not going to bother to train this. I'm just going to pick a random feature and threshold. and cut my data set randomly. What's the only thing I need to check here? The error. As long as this error is better than 50-50, that's okay. It's not maybe the best weak learner I can get. Like if I train it with a neural network or with a regression or with a decision tree, I get a smaller error. The smaller the error, the bigger the alpha t. So the bigger the impact is going to be. But even if I pick a random tree that's not a random tree, not a random performance tree, but some tree that has some error, which is not 50%, that was still going to make progress. Right? So I didn't need to spend a lot of effort training these things as long as I don't get close to 50-50. So in reality, I can pick initially random trees or random regressors or random whatever I want, because initially I won't be close to 50-50. But after a while, the distribution is going to focus in such a way that it's going to take a lot of effort to not be close to 50-50. Right? After I train 100 rounds of boosting, a random tree almost certainly will be 50-50. So I need to push the pedal of training something that will be better than 50-50. Right? That's a very good point. This procedure is independent to the actual training of the weak learner. So people have tried to combine all kinds of things. And algorithms like weighted majority, if you heard of it, or experts, multi-arm bandits of experts, giving opinions about things, and people looking at weather TV channels weathers and trying to figure out how the weather actually is going to be given 3 predictions. All those algorithms are intimately related to this procedure. They're particular cases of this procedure. Any bidding schema that I go to 3 casinos or 5 casinos and I try different things, allocating my money into different bids or different stocks in the market, so on and so forth, and next day I update my allocation to whatever stock performed better the previous day, I give it more money or less money depending on performance. They're all particular cases on this mechanism. This mechanism, theoretically, it's called hedge algorithm. And that's where the name hedge funds coming from. Because hedge funds are managed essentially by an online allocation process, right? The managers of hedge funds put their allocation into a lot of weak learners, that would be the stock markets or investment possibles. And they monitor the performance. Whoever does better, I'm gonna give it more money the next day. Whoever does not so good, I'm gonna give it less money. So the analogy, who would be our investments in here? The data points are the investments. And every time I do better or worse, I update who do I need to focus on, right? This distribution. So the name hedge funds comes from this online mechanism, which is the same mechanism that controls Adapus. It's not written this way, but the same principle. Online allocation problems, they're all based on this kind of formulation, and typically an exponential update. Okay, so now what do we have to do? We have to figure this out, right? Why is that? I mean, we said why it's important, because if we can prove it, that means training error goes to 0. I think everybody understood that, right? This is between 0 and something that goes to 0, therefore it must go to 0. But we need to prove that thing. Now the proof is not required for the course. It's not like during the exam, I'm going to ask you prove that for me. But you should be able to follow it. So let's see. Like before, if we get stuck in details, I'm going to leave it at that and say somebody can unstuck me for next time. But at least I want to go through the main math that's happening here. So first of all, who's the training error? That is the probability. No, forget the probability. We already said what it is. It's the sum over all data points, D1I, that is the 1 over n, because D1 is uniform. xi times an error every time this is not y. Again, this value is 1 over n initially. So this says here, this is smaller than sum over all data points d1i exponential, so e at, right? Minus yi f of xi. That's one thing that we have to check why that is. And then he's saying this thing is the sum for I equal 1 to all the data points, right? Of d t plus 1. That is the last distribution, right? D t plus 1 is last d. So I broke it step by step in here. Let's see step by step what's going on. I think some of these things here might be easier than others, but let's see. What happened from here to here? Obviously, d1 stays as d1. This is 1, I believe, yeah. d1 of xi. That's that. Why is it that this is smaller than this? So what happened here? This predicate being 1, this is 1 or 0, right? This is 1 when f of xi is not equal with yi, and it's 0 when f of xi is equal with yi, right? It's 1 for errors, 0 for it correct. This quantity 0, 1, so let's put it here. This is 1, this is a 0. It says it's smaller than e at minus y f of x. Why is that? Yes.
Are our yi's 0, 1 or negative 1, 1?
I don't know. Whatever works, I guess.
Because if they're
So I think this has to do with the signs. How we gonna predict f? At the very end, f is my linear combination of these trees, right? How am I gonna f is gonna be a score, it's gonna be a real number, right? So how am I gonna make a real number out of this? Assuming I'm not trying to find the threshold, I'm just gonna invent, threshold is 0. If the sign of f is negative, I'm gonna predict 0 or minus 1. And if the sign of f is positive, I'm going to predict plus 1. Right? So the actual prediction is 0 or minus 1 if f of x is negative, and 1 or plus 1 if f of x is positive, right? So how does it play out here? If f has the same sign as y, my prediction is correct or incorrect? Correct. And the sign, this thing is being a positive, is going to be e at minus something. And if the f has a different sign than y, then my quantity becomes positive, which means e at that will be at least. So I think we should do this case by case. If f of x is not equal with y, why is that? It's because they have different signs. f is positive and y is negative, or y is negative and the other way, right? But if they have different signs, what's going to happen here?
The negatives cancel and the rest of it.
I get a positive, but E at the positive quantity is bigger than E at 0, which is 1. What do you guys think? Case by case again? If those are different, E times F is negative, then with the negative sign, it's positive. E at the positive value is bigger than this one here. If they are the same, I don't have to worry about, because E at anything will be a positive quantity, right? So it's bigger than 0. Yes.
What if f and y are both positive but they're not the same?
But in that case, the prediction will be, if f is positive, I'm going to predict
Oh, okay.
true, right? So then I'm going to be right.
Okay.
If f is negative, I'm going to predict -1. So if they have the same sign, I'm going to get the prediction right. And no matter what I get here, this will be 0. 0 is smaller than any exponential value. Need some time to sink in? When I saw first this thing, nobody explained to me. I was just starting my PhD, because back then Adabus was not taught in machine learning classes, so I just did it as a PhD student. I didn't figure out why that is. I thought it's a mistake. How can this be? And until somebody explained to me, you just do it case by case. You know? So I think you have to think a little bit about this. I know it's easy when somebody says it, but think about for a while. This is a common transformation that's used when I want to transform a discrete 0, 1 thing into something that's always bigger than. So even if I increase some sort of lagging error here, it's a usual transformation for just cover both cases. So that's happening from here to here. How about from here to here? I had D1 times this. I guess I have to figure out who is this, right? How does this transformation from here to here corresponds to saying E at, who is this? Minus yi f of xi. Right? So I think this is the time for me to expand f and say, oh, okay, it's E at minus yi, that's fixed. Right? And who's f? F is the sum of alpha t ht of x. So now, do I get this?
Doesn't it end up working out that like you break the e if the sum of the exponent into a product of these, and then that product of these ends up being equivalent to whatever iterated probability you get in dt plus 1?
Right. So we have to think about how this in here, it's effectively, to get to dt plus 1, it's saying it has to run through all the updates of Adaboost, right? From D1, it has to go to D2, from D2 to D3, from D3 to D4. So at each update, what happened? I multiplied or divided E at alpha t, right? So this in here is a product, right? That's what you're saying, I think. It's a product of E at alpha t ht of x times minus y.
I think the y may stay out, and that product becomes the normalizing constant zt.
Let me see if I get it this way. Right. So my idea, I'm still running intuition here before I do details, is I start with d1 of x, and then I want to show that the e at the classifier times y is actually running all these updates. And I think I'm very close to show that, because e at alpha t, it's exactly the update. The only thing that's different is sometimes it's minus, sometimes it's plus. When is it a minus? When prediction is equal to y, which means what? H times y, h of x times y is what? If h is equal to y, they have the same sign, right? So if h times y is plus 1. Right? And in here, if h of x is different than y, h of x times y will be equal with minus 1. So I think you can see this. This is a product of epsilon t's, which are the updates. And this is exactly the plus 1 or minus 1 related to which ht's were correct for that point. Correct will be ht of x times y is a positive, but there's a minus in here. And then when it's incorrect, ht times y will be negative. With this minus, that will be a positive. So this exactly corresponds to the updates, right? Which means if I multiply this, if that's the updates, is the product of, let's call it update steps. Update step t of xi, right? The update is exactly that multiplication in there in the last step. So if this is the product of updates, what happens if I multiply with the initial distribution? d1x times e at minus y f of x will end up being the last distribution, right? The dt plus 1 is the last distribution that results here at the last step. That's not being used again because I stopped the algorithm, right? So at the last loop, since I run this to step t to big T, what's going to be the last distribution that I compute here? Last d is dt plus 1, right? Big T. If I run to round 100, the last distribution will be computed distribution d101. Except that's not getting it back into the loop because the process stops after that update, right? Who's with me so far? Questions then? Yes.
The product of ZTs is it like counteracts. That product of ZT comes from the normalization bit that we left out.
Right. We left out something. We say we run the updates, but the updates contain a divide by ZT, which I don't have. So it's the product of updates times the normalization factor because that updates divides by ZT, but I don't have a ZT in here. Right? So the update itself, it says you gotta multiply with this, which I have, and divide by ZT, which I don't have, so I have to put back that ZT in there. Right? So if somebody says multiply with 7 and divide by 5, and then multiply with 100 and divide by 20, if I only multiply with 7 and with 100 without doing the divisions, it's equivalent to call the whole update times back the denominators that I didn't use, right? The ZTs. Let's get back to this step. What I like here is that F is the sum of alpha THT. That's the ensemble. That's the linear combination of those weak learners or trees, whatever I have, neural networks, doesn't matter. Now, each one of those is, if I look at y multiply with h, that tells me correct or incorrect, right? Because y and h are either plus 1 or minus 1. So ht times y, for every round, on some rounds I'll be correct on this data point xi, and some rounds I'll be incorrect on this data point xi, right? I won't be correct on every single data point or incorrect on some data point all the time. For every data point, you remember the example last time, I was correct on some points, but then I changed the distribution, so my next weak learner was correct on different points. Right? So then this is correct or incorrect. This whole thing here is correct or incorrect. And then there's E at alpha t, which is exactly the update. That's why I'm going to get exactly the correct update, because this is E at alpha t. Either divide with it or multiply with it, depending on whether you are correct or incorrect at that round for that data point. So that's coming from there. ZTs I have to left out. Now, if that's true, when I multiply with D1, which is what I have here, if I run through all the updates, I'm going to get D1 times all the product of updates times ZTs, right? Because what I have here is the product of updates times ZTs. But that thing in here is going to be DT plus 1, right? Because if you start with D1 and you do all the updates, you're going to get the last distribution times the product of ZTs. Now, because this is a sum over the data points, what is the sum? This is a constant here, right? This product of ZTs, it's a constant with respect to data points. Whether it's inside the sum or outside the sum doesn't matter. It's the same ZT for every data point at that round. So you can take this outside the sum. And how much is sum of overall data points of dt plus 1 of xi? This is a distribution, right? Over all the xi's. The last distribution. So if I sum up over all the data points, I get 1. So what's left of this is the product of ZTs. Hands up, who's with me? Okay. As I said, this proof is not required, but we should follow it. We're not quite done, right? Product of ZTs is not what we want yet. We want this. We're getting close, right? I mean, we have product over t equal 1 to t of this square root, and here we have product of, this is from t equal 1 to t, not of the square root, but of zt. So we need one more step. Let's see. This is here the product of ZTs. So now who is ZT? Who is ZT? ZT normalizes this distribution, right? So you have a previous distribution dt, that's a distribution. I do the updates. And now for that to be the next distribution dt plus 1, I have to normalize those things. Sum them up, divide by the sum. That's what ZT does. It takes dt times this and says now you have a bunch of values that they don't sum to 1 anymore, because whatever this quantity is, so this quantity is 3. You divided by 3 a bunch of them, the ones that were correct, and multiply by 3 the items that were incorrect, right? Everything that's incorrect gets increased. Everything that's correct gets decreased. The quantity of increase or decrease is the same, the multiplicative factor. So some things, if this is a 3, some things gets multiplied by 3, some things divided by 3, but now the sum is not 1 anymore. So I have to sum them up, divide by the sum to get the distribution. So who's ZT? ZT gotta be that sum, right? ZT gotta be the sum over data points of dt of that data point times what? E at alpha t minus alpha t or plus alpha t, plus or minus. So alpha t times plus minus 1. What is this determined by? Some things gets divided by E at alpha t is the factor there, but who determines who's divided with and who's multiplied with? H of t, ht of x, right? And y together. If they have the same sign, that's correct, and they have to be divided by alpha t. And if it does have different signs, so this is correct, incorrect. So let's write this again. Sum of I equal 1 to n of all the data points. dt of xi times e at minus alpha t yi ht of xi. Is that true? So when yi and ht have the same sign, this product is positive, and in that case, I need a minus or a plus here? Minus, right? Because I'm in the branch that says correct, you got to decrease. When y, I, and ht have different signs, then the prediction at that round for this point is incorrect. That will be -1. Negative with a minus becomes here alpha. Right? So this controls correct or incorrect here. Is that the correct or incorrect? So now let's break that sum into two. I'm going to say sum over all I with the property that ht of x is y. That's correct, right? So I sum over all data points at that round. Some of them get correct, some of them get incorrect. So the ones who have correct, what do they have? dt of xi times e at minus alpha t, right? Because they're correct. Plus the sum of incorrect data points. That's the ones that ht of x gets the wrong prediction. That will be dt of xi times e at alpha t. So I broke these sums into the points that get correct classification for that round, the points that get incorrect classification. Now, I say this update constant factor here is the same for all points. All the points that, no matter what the distribution is, if they are correctly classified, they all got divided by 3. So I can take this and move it in front of the sum. I can do things on the whiteboard that you may not be able to do on paper. Right? Again, the idea is all these points have the same factor of being they correct, so they get lower distribution. And all these points get increased because they're incorrect. Right? But who is this? Sum of the distribution that ht gets correct. Let me ask you, who's this better? I sum up the distribution for the points that ht gets incorrect. Don't I have this somewhere on the board?
Epsilon t.
This is all the points that ht gets incorrect, sum up their d values. Right? It's exactly that. Look at all the points that ht gets incorrect, sum up their d values. So I think I'm summing up their d values for the points that are getting incorrect. I think this is epsilon t. Not with the alpha, just this part. And who's this? The sum of everything that I get correct.
1 minus epsilon.
1 minus epsilon. And who is this e at minus alpha t? We already said that who it is. What is that? Epsilon t divided by 1 minus epsilon t, like that? And who's this? This is backwards, right? 1 minus epsilon t with a square root divided by epsilon t. So now they think, how much is the product between epsilon t and 1 minus epsilon t times this? That's a square root. So if I bring this under the square root, it's squared. The whole product is epsilon t times 1 minus epsilon t, right? And in here is the same, just different. So this is square root of epsilon t times 1 minus epsilon t. So the whole thing is 2 square root of epsilon t times 1 minus epsilon t, right? Am I there yet?
Yes.
We can substitute 1 minus epsilon t with gamma.
No, half minus I.
Half minus epsilon. Half can be written as 1 minus.
So we can just substitute that gamma as half minus epsilon.
Damn. Not there yet. So okay, who's gamma? Gamma is 1/2 minus epsilon.
Yes.
Right, so I already showed that this is this value here, and I need to show that this is smaller or equal than 1 minus 4 gamma squared. Gamma squared is 1/2 minus epsilon squared, right? exercise? I kind of feel like moving on here. This is just high school, secondary school, if you come from Russia. Let's see if you guys can deal with this pure math, and if you cannot, we'll work it out. I'm sure this is a high school inequality, right? At this point, nothing to do with machine learning. Why is this true? The product, I have the product somewhere in here, right? This is a ZT, but I have a product over ZTs. So that will be the product over these squares here. But I'm missing this one step going from here to here. So this is, I'm going to say 1 in here because I don't have it. But it should work out pretty easily. So in my note says equal. So that should be even easier because equalities are always easier than inequalities, right? But again, apart from the math, which needs to be figured out, this is an elementary proof, like it could be done with high school math, that again, if you guarantee that the errors are not close to 50-50, aka gammas are not close to 0, training error must go to 0, which is an amazing guarantee for a simple method, right? Regression doesn't have such a guarantee, right? In fact, you can see why. You can ask for a line on a training set. Regression cannot possibly match all the points, right? I mean, just look at the points visually. They're not all on the line, so you put a line there, some of them will be off the line. Many methods cannot guarantee a training error equals 0. And that may be a good thing. The fact that regression doesn't get the training error equals 0, it means maybe it's less complex, that is less overfitting. I'm not saying that's bad. I'm saying in here, we can drive the training error to 0, assuming the weak learner does its job at all steps. Yes?
Like, this might be a little bit more practical, but is there any like better weak learner than other weak learners? Like, is there anything to do, like pick one?
The only thing I can say in generic sense, like without looking at data, is that in the beginning, you can afford more complex classifiers than at the end. So at the end, if you're down to overfitting, you don't want to use complex classifier. Any increasing complexity at the end of this ensemble, when you already learn as much as possible and the error starts very close to 50%, then increasing complexity here is probably overfitting is not worth the trouble. But in the beginning, to kind of speed it up, you can have more complex classifier because even if you run decision tree of size 2 splits in the beginning, that's unlikely to overfit, right? So I would say if you get stuck with the 50%, the real trouble here is if you run your weak learners and you get stuck at 50%, your temptation might be to increase complexity to drive the error down, but that's more likely to be overfitting than actual learning. So in my experience, if you have a reasonable good data set, say at least like span-based, what, few thousand data points and few tens of features, the moment you get, even with the weakest possible learner, like a decision stump, one-level decision tree, the moment you get to 50%, you're probably already overfitting at that point. So there's no point increasing the complexity of that classifier, it's just going to overfit more. So in the span base, you're going to get to 96% accuracy with decision stumps. Can you get it to 100% accuracy? Yeah, if you increase the trees, but then that's not going to increase the testing performance. It's going to just overfit. So I think to give you a more specific answer, we have to look at data. Pretty cool, huh? Again, this has been a breakthrough because most people believe it's not possible before this paper, Adablu's famous paper. Okay, now let's get down to computer science in reality, right? This is great. We can decrease the training error, which means learning. That's what learning is, right? Match the training features with the labels without increasing variance, which is in common sense overfitting, without being very specific to that training set. Great. What's the difficulty in here? You have to implement this supposedly now, but it's going to happen after the spring break. How do you have to modify your homework 1 decision tree code? What's the essential modification? The loop, it's easy, right? Just keep a distribution over data, update it, blah, 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 compute this, compute that. When you train, you're going to have to modify your decision tree procedure, a little bit to do what?
To weigh the
Makes
input
sense.
point by distribution.
Right, you only do stumps, but then can you just call homework one procedure?
No, no.
No, because of this DT here, right? Whenever you evaluate, decision trees are really brute force. You try a split and see what happens, try another split, see what happens, right? So when you keep track of what happens, the error, you gotta include the distributions in there. Your homework one doesn't have this DT. You just measure the error or information gain or whatever, and then you say, keep the best one. In here, you can keep that form, information gain, or some other thing you have, but you have to weight by the distribution that's available at each loop.
Couldn't we sample the data set with that distribution and then pass that sample into our decision tree?
Right. You can, and people have tried that in the sense of, I don't want to spend too much time training. That won't be a better tree, just faster.
Yeah, and
So-
you won't have to modify your code, because it still is getting some matrix.
But if you sample that, then if you sample that way, you have to sample with replacement.
Yeah.
So
want
if
an
you
alpha
sample with
data
that distribution, you have to allow for a point to appear twice, and I think samples have to be reasonably big. I mean, if they're not reasonably big, it's gonna be quite hard to match that DT. DT becomes very skewed at some point. Some things have very small weight and some have very high weight. Sampling is a problem when distribution is skewed, right? Because you have to sample a lot to match that distribution. If you take, I have 4,000 spam data points, and you sample 10 of them, your distribution will never match a very skewed distribution that has, for some point, 0.0001 chance, right?
Right.
I think most people just compute the error that way, multiply with DT, and keep track of the best error, and that's that. So that's an obvious disadvantage, that in brute force, like decision trees, maybe it's not a big deal because in decision trees, nature of brute force, this doesn't add a lot of computation. But if I am to run some fast algorithm, adding these T's in may complicate my running time of that algorithm. Also, once DT becomes in that skewed position that makes it hard to learn, the progress is very small, right? Once epsilon T's become close to a half, even though I make progress, progress is small, so I have to run a lot of trees. What you're gonna see is the first few trees do the main lifting, 3, 4 trees, and then the distribution gets in that skewed position, epsilon gets close to a half, alpha gets close to 0. To make progress, you need to train another 300 trees. Right? I mean, you say the target is 95%, you're gonna get to 91% in 3 or 4 or 5 trees, and then you need another few hundred trees to get to 96%. Right? Because the progress will be very, very small. So let me show you what other people have thought about this and said, that's all very good, but here's a different idea of how can I implement this. By the way, there is a much fancier paper which came 3 years after this one that makes a proof about testing error. This is about training error. Testing error needs an assumption that data in testing follows the same properties like data in training, right? Otherwise, I couldn't prove anything. If testing data is very different than training, of course, my model can have any error. But assuming testing data somehow looks mathematically like the training data, then there is a proof that's much more complicated why testing error tends to decrease. But what I want to show you now is a few years later, somebody figured out a much more easier way to think about this. Okay? And they actually didn't figure this out from a practical perspective, the way I'm going to explain to you. They figured out from a statistical gradient descent perspective. They said, let's look at this f of x, so let's call this now gradient boosting. Boosting comes from the word boost. Boost means what? Improve or increase the quality or the performance of a simple decision tree. Right? So boosting a decision tree or a decision stump means improve that performance by combining few of them. So somebody said, if I look at f of x as my matching y function, can I take gradients? I want to make a change in f based on gradient. So I think about, I have my current f, some number of trees, and I say, how can I change that f to so if I have a loss L that measures the somehow the difference between f of x and y, I'm looking at the differential of f with respect to f, and that will be my gradient. That's the idea. Of course, that depends on who the loss is. So if the loss is, say, 1/2 our typical loss, f of x minus y squared, this is going to be f of x minus y. The reason it's not the loss of integration is that here I'm not differentiating with respect to a regression coefficient. I'm differentiating with respect to the f function, so with respect to this guy. So my argument for differential is f. So you can easily see something minus a constant square when I differentiate is that something minus the constant square. So f minus y. So what this is saying is the change that you need is this column gradient. So a very smart mathematician, I think at Stanford, wrote this down for general loss function and general f's and all that, and leave it there. And then a computer scientist came after him and said, wait a minute, forget about all this theory. I mean, you can, we'll let you do the theory, fine. But you know what he really means? He means if f is currently a bunch of trees, like there, alpha 1 some tree, plus alpha 2 another tree, right? Plus alpha k another tree. He said this new tree here, let's call this hk plus 1. What this has to do, this tree, based on this gradient idea, hk of x should be y minus f of x. Let's forget about gradient descent for a moment. This is a very simple idea. It's saying if you can predict so far with your ensemble, this is f of x, right? If your prediction is not the label, what do I have to add to that prediction to make it the label? Exactly the difference, right? If I manage to fit my next tree to match the difference, what's going to happen when I add that tree to the example? I'm going to get the new f, fk plus 1. This is fk because it's f after k rounds, right? Fk plus 1 will be the fk plus my new tree, right? Let's assume the coefficient is 1. This alpha k plus 1 is 1 for simplicity here. So what's this going to be? It's fk of x plus y minus fk of x. That's going to be y, right? Isn't that exactly what I want? So what does this mean in practice? It means at every round, what do I have to do? Add a tree on the same data. I'm not changing the data set. I'm not reweighting the data set. It's the same data set. What I'm changing here?
Subtract the current prediction from all labels.
I'm changing the labels. Right? So at every new tree, I'm going to have a different label. Initially, I start with y's, and I try to match the y's. But I won't do it perfectly. If I do it perfectly, that's great, right? I get training error 0, I'm done. If I don't do it perfectly, I'm going to try to match a second tree. But this tree will not match the original y's. Will match the difference between y's and current f's. The reason to do that, the easiest way to see it, is to say, well, if I could match that, when I add it to my existing predictor, I'm getting back the y's. So this is called a residual label. So the procedure here will be match every h to the residual labels. And that works even better than other host. It will take less strings to fit that way. One reason is when some of these y's becomes close to f0, maybe my training procedure finds a way to not change those anymore. It's hard with a simple tree, but maybe if I keep the existing predictions that are correct, meaning f equal y close to 0, then I only have to focus on points that somehow are not correct yet. Okay? So this implementation is actually much easier than this one here. The algorithm for that will be a piece of cake, right? It's a loop that says, I don't have a distribution, right? Modify, so I have the y at this thing, so I get ht of x has to try to match the y, right? And then what do I have to change to make the update? I have to update the y's, right? So yt plus 1 has to be the yt minus ht of x. I go into next round, next round, next round. I fit to the new y's, so on and so forth. And at the end, f of x, it's still the sum of ht of x. In here, I don't have the coefficients. I skip the alphas. Much easier than this. So there's entire math with derivations about how that works. That's what I have to say about boosting. We're not done. So you don't have enough to do the homework, but you have enough to do a lot of the homework. So we'll have to wait for Tuesday to do the rest. But I want to throw one more idea at you related to this without explaining the whole idea. I'm going to do that on Tuesday. The idea, one of the problems that you have is related to what's called active learning. In active learning, the difference is not in the algorithm. The difference is in how do you label the data. Suppose you are given a budget. So instead of giving a training set of size 4,000, you are given a budget of 4,000 labels that you can choose which data points you label. So the training set comes without labels, but you are given a budget to say you can choose which 4,000 spam emails to label out of a data set of, say, 7,000, 8,000. Of course, whichever you label becomes your training set, because you can't learn from unlabeled data, right? One idea would be just label 4,000 at random, right? We don't know anything, so why not just pick 4,000 spam emails, and hopefully we get some spam and some no spam. We pass it through the annotator, the person who labels them. They look at them, we pay the money, and then we use that as a training set. Active learning asks, is there a better way to do this labeling? If you have a budget and you can choose which emails to label, would you pick 4,000 at random? Right. So the theory I'm going to explain when we see next time, but the idea is this. Suppose I've labeled 1,000, not 4,000, 1,000. And I already got a bunch of spam emails and a bunch of non-spam emails. And I train my classifier, say a regression, right? And now I have a lot of how many? 8,000 data points which are not labeled. But I know where those data points are. These dots are unlabeled data points. Again, I use only 1,000 of my budgeting label. Every label costs $1, so I have to pay $1. I label 1,000 at random. I train my classifier, that's the picture. Now I say I can label more data because I still have $3,000 to label data points, right? Everybody follows me here? Which point should I choose to label?
Just farthest from the moment peak.
This one here?
What's on the line?
That's the problem in your homework. If you can drive this label, which you still have, everybody have the same budget, 4,000. And so far in our data sets, this came labeled to you. You had no control what data points get labeled. We label them for you and you have to deal with them. Now, you're gonna simulate this. Of course, you have all the labels, but you have to pretend that you choose which ones are labeled, adding to the training set. The question I have, is it worth labeling this one, or it's better to label this one, or this one, or which? And again, I probably don't want to use all 3,000, right? It made more sense to use another 500 or another 1,000, redo the classification, and then ask the same question again. Which data points will make the biggest difference? I don't want to answer the question today. I just want to pose the problem. But I'm going to say this. How much information do I get by labeling a point in here?
Very little.
Chances are, this guy is a what?
Outlier.
It's a high chance that's a plus. If this ends up being a plus, I pretty much wasted my money. Because if this is a plus, I didn't learn anything. See, there's a bunch of classifiers that are all possible in here, viable classifiers, right? I learned one, but all these are possible. If I'm asking my classifier through labeling, I want to slightly adjust this line to make it better, this point won't make a difference. If this ends up being a plus, I'm not learning anything, my line will be the same. If this ends up being a minus, it's probably an outlier. Because if I include this outlier, it's going to change the line a lot, but it's very unlikely, right? My point is that maybe this is not the best data point to label in terms of how much information my regressor or neural network or decision tree can get out of it. It turns out, so you're going to have to deal with which points to label, that this is an extremely effective procedure. The number of points that I need to label to obtain a certain performance, it's a lot smaller. So suppose I want performance 85%. How many points do I need to label randomly, as in just pick a bunch of them and label them, versus how many points do I need to label intelligently by doing this stage operation? I need a lot less points if I pick them dynamically. So by the way, last thing I'm going to say, this happens naturally. You ever get called by a credit card company and say, hey, we think there's a problem with your credit card, maybe fraud? That happened to you? What kind of point in that one? There's a machine learning algorithm that flags that as possible fraud. You think that's in here?
No, I'm certain.
It's probably in here, unless it's actual fraud. Most of the time it's not, right? So that point is a point that's more useful for their learning. Of course, the most concern they have is fraud or not fraud. But to be a useful point for machine learning is probably not one that's far off. Most flu patients are treated by a nurse, right? Nurse people are not paid that much money. Every once in a while, a flu patient is treated by the actual doctor. Who do you think is that patient that's treated by a doctor in that table?
Not sure if it's fully on.
So every time more sophisticated intervention is necessary, it's probably one of these interesting cases. All right. Have a good spring break. We'll announce some of the results. And I'll see you after that.
This is alpha team.
Oh, okay. I'll follow that.
So does it act like a learning
Is it all right?
But your code should be.
Yeah,